So I want to see if we can do a video on 4.3 notes, dividing polynomials, the remainder, and factor theorems. The idea is that you can divide polynomials using long division and synthetic division. There are times when long division doesn't work, or synthetic division doesn't work. We need to use long division, although I will be giving an alternative to long division as well, because there's more than one way of doing it, as I learned just a few years ago from one of my colleagues. So here's the problem. X squared plus 4x plus 5 is divided by x minus 3. Well, if x minus 3 went in there perfectly, I could just factor the thing, but it doesn't go in perfectly, so we're going to divide using long division. So here's the way this works. We put x minus 3 on the outside of a division bar, just like if you were dividing stuff, right? You guys remember how to divide things. If you were dividing, let's see, if you were dividing 3 goes into 176,582 or whatever it was, you'd say, oh, 3 goes into the 1. 3 doesn't go into 1, but 3 goes into 17. 3 times 5 is 17. Well, 3 times 5 is the closest thing I can get to 17. Remember? Do you remember doing this? 3 goes into 17 5 times, and you multiply 3 times 5, and you get 15. And you subtract and bring down the next number. 3 goes into 26. Let's see, 8 times. 8 times 3 is 24, and so forth. You keep on doing that. You subtract, and then you bring down the next thing, and so forth, or the next thing is a 5. And then you keep on going and going and going until you're finished and you have a remainder. It's very similar with polynomials, except they're polynomials, so they act a little bit different. So for instance, with my numbers that I had on the outside, you say, well, I can't really do x minus 3 completely, but I can look at the x part. I can say x goes into x squared. Well, how many times does x go into x squared? X goes into x squared x times, because x times x is x squared. Now, if you remember the way we did it with numbers, you take that x on the top and you multiply it by the entire thing on the outside. X times x minus 3 is x squared minus 3x, which we're then going to subtract because that's how you divide. So I got this x squared minus 3x by multiplying x times x and x times 3. Now, subtracting these things is the same as adding and changing the sign. So I usually do that so I can see what's going on. If you do this correctly, your leading term will always go away. So x squared minus x squared is 0, and 4x plus 3x is 7x. So I'm going to bring down the 7x and then bring down the next term, just like with regular division. Then I say to myself, x goes into 7x. Well, x goes into 7x 7 times. 7 times x minus 3 is 7x minus 21, because you distribute 7 over x minus 3. Subtracting this from the thing above it, 7x minus 7x is like it's supposed to be. It's supposed to be 0, but we have a leftover of 26. So 26 is a remainder, but a 26 is a remainder meaning what? Well, 26 of x minus 3. If I had a remainder in a problem with numbers, I didn't get that far with the problem I was doing. But if I was doing, let's just do into 17. 3 goes into doesn't go into 1, but 3 goes into 17 5 times. If you subtract this, say, oh, 2 are left over. 2 what? Well, they're 2/3, right? Because you're dividing by 3, so it's thirds. So that's what you do. So it's the same thing here. The divisor is x minus 3, so that's what's left over. Okay, there must be a racing stuff. No? Erase all ink on the slide. There we go. All right, so if we're going to do this one, before you start to do this one on your own, what I'd like you to do is I'd like you to keep some, well, you can try it on your own first if you want. Go ahead and try it on your own. I'll get it set up for us. All right. So either you've paused and tried it on your own, or you're going to do it with me. That's fine. Or you're going to do a combination, which is also fine. Notice that on this problem, I put a 0x to the third here. I don't really need to, but just because if there's an x to the third missing here, I wanted to leave space for it because otherwise it might get kind of messed up. So I'd like to leave a space for that so that I can see what's happening. So like in my last problem, I say x goes into 3x to the fourth. Well, x times what makes 3x to the fourth? That's really what I'm asking. X times what makes 3x to the fourth? The answer is 3x to the third, right? Because 3x to the third times x would make 3x to the fourth. So we're going to multiply 3x to the third times x plus 2. So I'm going to get 3x to the fourth plus 3x to the third times 2 would be 6x to the third. That's why I wanted to leave a space for that x to the third. You didn't have to write 0. You could just make a space if you wanted. And that would have been fine too. Now, subtracting this means subtracting that and subtracting that. So 3x to the fourth minus 3x to the fourth is gone like it's supposed to be. And I get negative 6x to the third. And I'm going to bring down the next term. All right. You might try the next step on your own, or you can do it with me. So x goes into negative 6x to the third how many times? In other words, x times what makes 6x to the third? And the answer is minus 6x to the second. So negative 6x to the second times x is negative 6x to the third. Negative 6x to the second times 2 makes minus 12x squared. All right. Now we're going to subtract by changing these signs again. That's what subtraction means. Minus 6x to the third plus 6, those are gone. And if they're not gone, there's a problem. Minus 5x to the second plus 12x to the second makes 7x to the second. And I bring down the next term, which is an 8x. Try the next step. X goes into 7x to the second. 7x times, multiplying 7x times x plus 2, I get 7x to the second plus 14x. Subtract by changing these signs. These are gone. I get 8x minus 14x is minus 6x. Bring down the next term, which is our last term. Notice that every time I bring down a term, that it's one less than the thing before it. So for instance, these work out, when I bring down the next term, it's always one lower. So this is 6x to the third, this is x squared. This is x squared, this is x to the first. This is x to the first, there's no x's on that one. All right, last step. X goes into negative 6x minus 6 times. Negative 6x minus 12, since I did negative 6 times 2. Change my signs. That's the step that people will forget because that's the kind of weird step. The x's are gone and we're left with 13. 13 is a remainder of x plus 2. So that's my final answer up on the top there. 3x to the third minus 6x squared plus 7x minus 6 plus 13 over x plus 2. That's our final answer for this division problem. Pretty horrible, but it's really the same thing going on over and over and over again. What the goes into step, the multiplying step, the subtracting step, the bring down step, and then the multiply, the goes into step, the multiply step, the subtract step, and the brings down to step. So it goes over and over the same way every time. So for dividing long division versus synthetic division, it's important to know that if you have, basically they're factors and there are roots. So for instance, if I have a factor of x plus 3, that is a root of negative 3. Or if I have a factor of x minus 6, that gives me a root of 6. A root of negative 1 gives me a factor of x plus 1. And a root of x of 1/2 really gives me a factor of 2x minus 1, since that's how I would get 1/2, right? I'd add 1 divided by 2 to get 1/2. So I'm putting this out there because to introduce synthetic division, which is really like synthetic substitution, we need to know what part to use. So for this problem, we're going to do it synthetically. Dividing by x minus 3 is going to be putting a 3 in the box. Remember this from section 1 when we did synthetic substitution. The 1, 4, and 5 come from the coefficients of x squared and 4, x, and 5. So if we were doing this problem if we were doing it as synthetic substitution, we would do it exactly the same way. We would set it up this way, but we're just going to interpret our answer differently. So if you remember how this works, the 1 comes down underneath the bar, multiply it by the 3. 3 times 1 is 3. Then 4 and 3 is 7. 3 times 7 makes 21. 5 and 21 makes 26. Now, the last time we did this problem, we got this answer. It's the same answer now. If we were evaluating x squared plus 4x plus 5 for when x is equal to 3, our answer would be 26. But since we're dividing, we're going to interpret what's below the bar there differently. We're going to say, since this top thing is an x squared, represents an x squared, what we're going to do is we're going to say, if this is x squared and we're dividing by an x value, x to the first power, this is 1 power less. So if this was an x to the fifth, this would be x to the fourth on the answer. If it was an x to the third, it would be, and so forth. So synthetic division is fine when you're dividing by a power of, or x to the first power. So this is exactly the same problem we got when we did this originally. Remember, when we did this problem over here, we got x plus 7 plus 26 over x minus 3. But I think that doing it synthetically was a lot easier, although it worked about the same way, right? So we did this synthetically by setting it up as dividing by x minus 3 is like having a synthetic division by positive 3 on the corner there, and it's the 0 of the thing. So let's try this one. This should give us the same answer as well, but when you're setting this up, it's really super important to leave the 0 for the x to the third, because otherwise it will not work out right. See if you can set it up first. So those are the numbers, those are the coefficients, and what's the number in the box there? Did you put positive 2 or negative 2? I hope you put negative 2. So go through and do the synthetic division. So here's what I get. Bring down the 3. 3 times negative 2 is negative 6. Add them up. Multiply by negative 2 to get 12. 12 and negative 5 makes 7. 7 times negative 2 is negative 14. Add them up. Multiply again, and so forth. Now, the 3 in the top here represents 3x to the fourth. So this down here is 3x to the third, 1 power less. And then we're just going to go descending from there, 3x to the third, or x to the second, x to the first, and no x's. And that 13 represents 13 over x plus 2. And that's what we got the last time too. So hopefully that's what you got this time, doing it synthetically. So the synthetic substitution, synthetic division are identical, except for how you interpret your answer. When we did this problem in section 1, the question was, what is f of negative 2? F of negative 2, put a negative 2 in there, and your answer ends up being 13. In other words, when you put negative 2 in for x, you end up with 13. But now we're interpreting the answer differently. It's the same work. That's the beauty of it. So when I talk about the remainder theorem, when a polynomial f of x is divided by x minus k, then the remainder of f of k is r. That's what I just said before. In the last problem, I said f of negative 2 is 13, right? So f of negative 2 is 13. That's what we're saying here. X minus k as a factor gives a 0 of k. When you put that in there, that's equal to the remainder. So dividing by x minus 2 gives a remainder of f of 2 is equal to 15, like the last example, except the last example was 13, right? How does this information help us? Well, if we wanted to factor, we would look for divisors that give a remainder of 0. If there is a remainder of 0, that means that the that the factor is actually the what we're dividing by is a factor if there's nothing left over. If there's a remainder, it's not a factor. It doesn't go in there. It's like 3 goes into 8. Well, 3 goes into 8, but it doesn't go in without a remainder. 3 goes into 9, no remainder, and that means that 3 is a factor of 9. So it's the same thing with polynomials. Zeros are roots. Not all roots are zeros, but all zeros are roots. A polynomial f of x has a factor x minus k if and only if f of k is equal to 0. That's using the remainder theorem to apply the factor theorem. Basically saying if you want to find out whether k is, if x minus k is a factor, it has to have no remainder. That's what this is basically saying. So let's see, find all the factors of this thing, 2x to the third plus 9x squared plus 3x minus 4, if x plus 4 is one of the factors. Well, if it's one of the factors, let's go ahead and divide that thing out synthetically and figure out what's left over after you divide out x plus 4. Go ahead and do a synthetic division on that thing and figure out what's left when you divide out 2x to the third plus 9x and so forth. So let's see, if it's x plus 4, I'm a factor, that means that the root is negative 4. Sure enough, there's no remainder, which means that x plus 4 is a factor. So I'm left with 2x squared plus 1x minus 1. That minus 4 represents x plus 4. But the question is, can you factor 2x squared plus x minus 1 into two parentheses? Remember your old factoring days? Or you could keep on going synthetically, but I think that that's pretty easy to factor that thing since 2x squared has to be 2x and x, and negative 1 has to be 1 and negative 1. So it's just a matter of getting the signs right. So to find all the factors of 2x to the third plus 9x squared plus 3x minus 4, and we know that x plus 4 is one of them, we can divide that out and then factor what's left. Some people want to start back over at the beginning and look for other factors. That doesn't make any sense. If you were doing a prime factoring on a number, like for instance, if you were prime factoring 20, well, let's find all the prime factors of 20, right? You would say 20. Oh, well, I know 2 goes into 20 10 times. You wouldn't start back up at the 20 if you wanted to look for more of them. You'd start with the 10 because that's still got more factors in them, right? So even though 5 goes into 20, we're not looking at 20 after we've divided out something there. Same thing is true with this thing. This is a cubic. Why would we go back to the cubic if we're looking for, if we know that x plus 4 is a factor? We're just going to factor from there, just like we factor with like prime factoring.